All right, let's talk about the holy grail of energy. I mean the real deal, nuclear fusion. It's the very same process that powers our sun and every single star in the universe. And for decades, it's been the ultimate prize for scientists.
So let's just start with a huge question. What if we could actually harness the immense, clean power of a star and build a tiny version of one right here on Earth? I know it sounds like something straight out of science fiction, but this idea is way closer to reality than you might think.
So at its very core, what we're talking about is recreating the engine of the sun here on our planet. And if we can do that, we unlock the ultimate promise of clean energy.
Today, we're going to explore what nuclear fusion actually is, why it's been so unbelievably difficult to achieve, and how a recent breakthrough has completely changed the game.
Okay, before we go any further, we have to get one really important thing straight. You've probably heard of nuclear fission, right? That's how today's nuclear power plants work. But fusion, well, fusion is a completely different animal, and understanding that difference is absolutely crucial.
So nuclear fusion is all about, well, fusing things together. You take two super light atoms, we're talking about types of hydrogen called deuterium and tritium, and you force them to combine using just an insane amount of pressure and heat. When they finally merge into a heavier atom, bam! A massive amount of energy is released.
And that right there is the fundamental difference. Fusion combines light atoms. Fission splits a heavy one. See, fission takes a big, unstable atom like uranium and just tears it apart. Fusion does the complete opposite. It's about building something new, not breaking it down.
And this difference has enormous consequences. For starters, the fuel. The main fuel for fusion, deuterium, can be pulled right out of ordinary water. It's basically everywhere. And the waste? It's pretty much just harmless helium. Now compare that to fission, which needs limited uranium and creates all that long-lived radioactive waste. I mean, the contrast is just night and day.
So, you might be wondering, if fusion is so great, why aren't we using it already? Well, that brings us to our next big topic, the absolutely mind-bending engineering challenge of trying to contain a star here on Earth.
Just think about that question for a second. It's the central problem scientists have been wrestling with for over half a century. No physical material, nothing we can build, can survive that kind of heat. So how do you even begin to make a container for it?
Okay, here's the number we're dealing with. 100 million degrees Celsius. Let that sink in. That is more than 6 times hotter than the core of the sun itself. It's a temperature so extreme that you need it to overcome one of the most powerful forces in nature.
At temperatures like that, matter stops being a solid, a liquid, or a gas. It turns into a fourth state called plasma, basically a superheated soup of charged particles. You need that crazy energy to force atomic nuclei, which naturally push each other away like magnets, to finally slam together and fuse.
So how do you bottle a star? You do it with magnets, incredibly powerful magnets. That's what this is, a tokamak. It's this giant, donut-shaped machine that creates a massive magnetic field to trap the plasma and hold it, suspended in the middle, so it never actually touches the walls of the reactor. It's quite literally a magnetic bottle. For decades, building these tokamaks has been a slow, difficult, expensive process. But then, recently, something shifted. Scientists finally hit a critical breakthrough, one that proved the fundamental science actually works.
You know, there's been this long-running joke in the physics community. It's captured perfectly by this quote. For as long as anyone can remember, viable fusion energy was always just 30 years away. It was this goalpost that just kept moving farther down the field. So what was the one thing, the one milestone that could finally prove fusion wasn't just a fantasy? It all came down to this one crucial question. Could we finally get more energy out of the reaction than we had to put in to start it?
This concept is called net energy gain, and it has been the absolute holy grail of fusion research. It's the tipping point. Getting even a little bit more energy out than you put in proves the whole principle is sound.
And they did it. It happened. For the first time in history, scientists at the Lawrence Livermore National Laboratory created a fusion reaction that achieved net energy gain. I mean, look at this. More energy came out than went in. After decades and decades of work, that moving goalpost was finally reached. The science works.
So, what happens now? What does this breakthrough really mean for us and for the future of our entire planet?
This breakthrough points toward an incredible future. I mean, think about it. A power source that's inherently safe,
A fusion reaction can't melt down, it just stops. Fuel that comes from water, massive amounts of carbon-free energy, and almost no long-lived radioactive waste. This isn't just another option, it could be the solution to our planet's energy needs.
Now look, commercial power plants are still years away, but the path forward is finally clear. The breakthrough has been made. Fusion offers this incredible hope for the future, a way to power our entire civilization, cleanly and sustainably. It's the hope of a future powered by a star that we built right here on Earth.
The promise of nuclear energy is enormous, but one colossal problem remains: nuclear waste. It's highly radioactive, heat-generating, and remains hazardous for millennia, posing one of the greatest long-term challenges in modern engineering and environmental science. In this first four-part series, Tracking Nuclear Challenges, we'll dissect the core issues we face today, from the complexity of different waste types and their immense half-lives, to the technical and political hurdles of site selection, long-term storage, and disposal financing. We'll explore why this small volume of material demands such extraordinary global precautions. Join us as we lay the groundwork for understanding the ultimate question: what to do with the nuclear waste.